iHex is a 6-foot walking robot that works in energy-limited environment. We analyze its power consumption versus working speed, like geometries and gates. By applying conservation of energy, we only need to consider the mechanical energy of the robot instead of integrating the force over displacement. In our design, the body does not move up and down, and it moves forward with constant speed. Besides, the 6 legs are identical, and therefore we only need to consider the mechanical energy of one leg. To simplify the design, we neglect the damping and the electrical resistance. We analyze the energy consumption of iHex against the walking speed, which varies from 2 centimeters per second to 10 centimeters per second. And the results are shown in this figure. The x-axis is the walking speed in centimeters per second, and the y-axis is the energy consumption per unit moving distance. Interestingly, the energy consumption does not simply increase with the increasing speed. This may be due to the natural frequency of the lag. This plot shows the mechanical energy of a lag within one cycle. The patterns of energy distribution over time are different at different speeds. This may explain the local minimum of the energy consumption.
So I was the lead leg length analysis researcher, and my work was to vary the different leg lengths, the upper leg as well as the lower leg, the thigh and the calf, to see the effects on the energy consumption of the robot. So we varied the different combinations. We had to make sure that the leg lengths were fairly similar, because for large differences the robot was unable to move. Based on our results, we found that the lower leg has a greater effect on the energy consumption than the thigh does. In addition, the energy consumption is lower for smaller leg lengths, which would lead us to believe that the smaller leg lengths would be essential for an optimized robot.
It's a reasonable guess that the gait would affect the energy performance of the robot. 3 types of foot tip trajectories, the rectangular, the triangular, and the trapezoidal one, are used to investigate the influence of the gait. For each trajectory, 2 moving strategies are implied. The first one is letting one leg moving each time, while the other one is letting 3 legs moving together. The energy of each leg changes within the cycle. In our model, the potential energy is comparatively large, which is represented by the peak in the figures. The result shows that the triangular trajectory gives the lowest energy consumption. This is because with the fixed step size, the triangle gives the shortest travel distance and the lowest reset velocity. Thus, the energy wasted in acceleration and deceleration are reduced.